right. In today's lecture, we are going to look at just a very brief summary on the introduction to the laser physics. All right. So this material is taken from Laura Corner from the Cockcroft Institute for Accelerator Science, Liverpool, and the CERN Accelerator School. So let's start. So we are going to, these are some of the reference materials where you can see, see the different things that where you, for example, lasers and principles of lasers, etc. So we will cover that what is a laser, the basic laser physics, and the different types of laser systems. So laser is the acronym for light amplification by the stimulated emission of radiation. So you can see that it is light amplification with the stimulated emission of radiation. We'll see what that means. We are all familiar with lasers, light from laser pointers to eye surgeries where lasers are done. And the materials that we are going to cover later, like PIV, LDV, PDPA, they all use lasers in one way or the other. So it is almost mission critical to have lasers as a part of your suite of measurements. And that is where we are coming from. Laser has got many other utilities also, which you already know. Even the supermarket scanners are made out of lasers. So what makes the laser so special? That when you actually have a simple light source, like for example, a bulb, incandescent bulb, so they give out beams in, beams comes out like this. Okay. And not only that, these lights are typically very incoherent and they are not monochromatic. Okay. So in other words, when a bulb actually emits something, it is very different from what we, so like for example, your normal room light will be very different. When you actually have a laser, they produce what we call a directional beam. This is the beam is in all possible directions. It produces a directional beam. If you compare the spectrum, you will find that a normal light, incandescent light, will have intensity across multitude of wavelengths. So it is basically not a monochromatic source at all. So it is given by some kind of a spectrum. So at each wavelength, it will have some intensity of irradiation. And that is what is typically plotted here. This is a cartoon. Whereas if you have a laser, you will see that all this becomes like a narrow line. This is, of course, what seems like a line actually has a little bit of a width associated with it. But for all practical purpose, the line width of this particular laser is much, much narrower than what we are, what we have experienced with, say, white light or incandescent light. Okay, this, however, remember, does have a little bit of a width. That means there is a little bit of a range of wavelength that is here as well, though it looks like that it is lasing at a single wavelength. So nothing is exactly at a single wavelength. There is a little bit of a wavelength change even in the case of a laser as well. Okay, and on the top of that, as we already said, that the laser is coherent. Okay, spatially and temporally they are coherent. Whereas a normal light source, as we know, we already covered what is spatial and temporal coherence. The coherence is actually destroyed in a light source. They are typically of the order of femtoseconds, the temporal coherence. Okay? So this is of no use. We need lasers, and you can maintain the phase and all those things over very large distances as well. So, and over longer period of time, almost of the order of a second. So few features are, it is directional, it is almost monochromatic, and they are coherent. This is what makes the laser so special. So basically, in order to understand laser, you have to understand a little bit of quantum mechanics. And basically, it comes from the two-level system description that was advocated by Albert Einstein. So what Einstein did was that he identified three ways in which an atoms and molecules can exchange energy with a radiation field. This we will also cover when we actually do our lectures on TDLS, or tunable diode laser based absorption spectroscopy. This we have already covered in details in our statistical thermodynamics course. So this is just a little bit of a heads up that what is coming. So the first one is what we called absorption, or basically stimulated absorption. So what happens is that when a photon of a particular color of a particular, of the correct energy actually is incident on a two-level system. So this is a two-level system. This is level 1, this is level 2. So what happens is that the electrons can actually absorb this, this energy and actually can go to the next higher energy level. Okay, so so that is what it is, called. So let me just stack this up a little bit, because I think this is what absorption is all about, so that you can see properly. So when we talk about absorption, this is what absorption is. So this is n equal to 1, this is n equal to 2. So what happens is that when a photon, which is h nu, okay, impinges on this particular system, what happens is that the electron from the lower energy level is promoted to the higher energy level. So this is called absorption or stimulated absorption. Okay. Now, in what happens, so this is when an electromagnetic radiation actually impinges on the system. So that means this is basically electromagnetic radiation interaction with matter, the light interaction with matter. This is what happens. Now, there can be another case in which you have what is called spontaneous emission. In this, there is no electromagnetic radiation that is needed. So the electrons that are there in the higher energy levels, they are basically unstable over there. Okay, so they have a very short lifespan, typically of the order of 10 to the power of -8 to 10 to the power of -9, or 10 to the power of -7 also sometimes. So it's about 100 nanosecond is the time that the electron spends in a higher energy level where it is unstable. So it comes back to the lower ground state and it releases the photon of the same color or the same energy as it was impinged. Okay, so this has got a particular requirement of photon, so it gives out photon of a particular energy only. All right, so this comes from this level to this level. All right, so this is called spontaneous emission, does not require interaction with radiation per se. This actually requires interaction with radiation, electromagnetic radiation, which promotes the electron from the lower level to the higher level. There is a third process, which is called the stimulated emission. Now, what is stimulated emission? In stimulated emission, what happens is that there is already an electron which is there at the higher energy level. A proton comes or a photon comes and bumps this electron from that level to the ground level, because remember, this was unstable here already. So it just requires a little bit of a push. Now what happens is that two photons gets emitted. These photons are coherent. They actually have the same, so therefore they have the same phase. They are emitted in the same direction. So this is what is called stimulated emission. So you give one photon, you get two photons out of the system, which are coherent to begin with. Okay, remember the word coherent. In the case of spontaneous emission, if you have multiple systems which is undergoing this spontaneous emission, the direction of the photons will be all around. Okay, so but why does spontaneous emission happens? This is because of the vacuum perturbations that are there in the system. That means the electron is basically residing in a very unstable position. Imagine that this is like a stone at the top of a mountain cliff. So any small push in either directions would actually land the particle or the stone into the ground. So these small perturbations, which are always inherent in the system, is what makes the electron undergo spontaneous emission, even in the absence of stimulated emission. Okay, and the lifetime of the electron, therefore, is about 10 to the power of is about 100 nanoseconds or so, very unstable. But the emission that is created is multidirectional. As a result of that, you cannot really, use it for any meaningful purpose. You can use it for other purposes, for something which is called emission spectroscopy, but not in this particular case. Whereas stimulated emission means the photons that are produced are basically coherent, and they basically knock the electron off, and so you therefore get two photons coming out of it. This stimulated emission is basically the S and E of the laser. All right. Okay. So As you can understand now, so these three processes, absorption, spontaneous emission, and stimulated emission, are the ways in which atoms exchange energy when it is interacting with a radiation field or not. Okay, so the rate of absorption or stimulated emission is dependent on the number of photons and the number of atoms in the upper and lower state. Okay, so this upper and lower states actually determines, and the number of photons that are impinging on the system, that is what actually determines. So the number of photons, also the photon needs to have the correct energy. It needs to have the energy of h nu, so that means it needs to have the correct color. Okay, if it does not have the correct color, then what will happen is that it is not going to promote, in the case of, for example, in the case of absorption, it will not be able to promote the electron from the upper to the lower, from the lower to the upper energy level, and it is not also going to be able to knocking off the electron from the upper level. You won't have two photons of exactly the same color. So the photons needs to have the correct energy, and the number of photons can be actually amplified. Okay, so you just having the photons of the wrong color and having a lot of them essentially does not do anything to the system. So you need to have the photon of the correct frequency, because without that, that means the correct color, without that you cannot promote absorption or stimulated emission. So this is one of the prime thing that you should keep in mind. And you can have millions of those photons, it absolutely will not do anything to the system. All right. So in a laser, the basic idea is that you want a lot of this stimulated emission. That means you want to have this avalanche of photons which are coherent, coming in a particular direction. We want actually lots of this, but you do not want a lot of absorption. Okay, because when a light is impinging, you have a probability of this as well as of this. Now, because it is dependent on the number of electrons in the two states, you see, if you have, say, more electrons here, okay, in the ground state than in the excited state, what will happen is that you will have more absorption, because the probability of this photon interacting with an electron and promoting it to an upper energy level is much higher than the photon actually knocking off an electron from the upper energy level to the lower energy level, because this level is already has lesser number of electrons to begin with. A system in thermal equilibrium will have an arrangement in which the ground state will have the most, and then you will have progressively lower number of electrons in the upper energy states. So the chances of stimulated absorption will be much more than stimulated emission. But in essence, for lasing to happen, you want more of stimulated emission, because that's why the photons comes out as a coherent beam. They are lockstep with each other, but you do not want a whole lot of stimulated absorption, because that is not your prime thing, because once it goes up, it has only 100 nanoseconds time before it comes back, giving out radiations in all possible directions, which we cannot use. So in essence, what you need is, you need more number of electrons in the upper energy level than in the lower energy level. In other words, you need what we call a population inversion. That is, more number of atoms in the upper level than in the lower level. This does not practically happen, because for a system which is in thermal equilibrium, this is basically N2 by N1. Okay, this both is written as N2. So this is the population graph that you normally see. So you see the most number of electrons will be at the ground state, and progressively it is like a well. It's like an exponential function that you can see. In thermal equilibrium, this is what will happen. But what you want is basically you want to create an inversion state. That means you want to pre-populate a particular state, okay, so that the number of electrons in that particular state is more than the corresponding ground state. Then what will happen? Then if you have the correct photon impinging on this particular system, what will happen is that the chances of stimulated emission will be much more than stimulated absorption, or absorption in general. Okay, so this is what we emphasized over here, because the probability otherwise will be more for this to happen rather than for this to happen. So if you populate and create a population inversion, the chances of a photon knocking off electron from the upper to the lower energy level is much higher, and therefore the probability of stimulated emission will be much higher than absorption. And this is exactly what is shown over here, that normally the states are like this, but you need to create an inversion. That means you need to artificially increase the population in a higher energy level than the corresponding lower energy level. Okay, because otherwise in thermal equilibrium, a system in thermal equilibrium will not have this. So you need to basically pump, to add energy to the medium. This is called a gain medium. Where the electrons are actually residing is a gain medium to get such an inversion to happen. So that means you need to add energy to achieve this, because you need to promote a few electrons from the lower energy level to the higher energy level, and by laws of thermodynamics you need to add energy to achieve that population inversion, which is rather unusual to begin with. Okay, now so this is the pump mechanism. So you have N1 and N2. N1 is the number of electrons, say, at the ground level. N2 is the number of electrons at the upper level. When you are saying electrons, it can be molecules, it can be other things as well. So the rate of population, so you are by green upward line, you are basically pumping electrons from the lower energy level to the higher energy level, and then by then the photons that are impinging is going to knock it off, and you are going to have the lasing. So the rate of population change, of population is proportional to the population density multiplied by the pumping rate. So the absorption and emission are equally likely. What we can do, best we can do, is basically N2 can be made equal to N1. So there is no population inversion if we use a two-level system. So two-level system, this is the maximum thing that you can do. Okay. So the two-level system is no good because you cannot achieve a population inversion. Hence we go to 3 and 4 level systems. So what happens in a 3-level system, for example, okay, so you basically use a pump which makes the electrons go from state 1 or ground state or ground level 1 to ground level to level 3. Okay, so there is an intermediate which is closer to 3. There is an intermediate level which has an energy E2 and a population, the number of particles N2. So what will happen, that in this particular location, the state is very short-lived. So this will go down to this metastable level, where using a very fast and radiation-less transition, more like heat rather than a radiation. And then here at level 2, what you have, this is the metastable, where the electrons are kind of stable up to milliseconds. So this acts like a hold place. This is like a hold where the electrons will be kind of at a metastable state. Okay, so that is rather important because this is what a 3-level laser system actually does. So it pumps and pulls it to E3. There is a fast radiation-less transition to E2, and from E2 to E1, it's a slow, and this is what the lasing function is all about. So you cannot get a population inversion in 2-level systems. So the lasers broadly are categorized as 3 or 4-level systems. So in a 3-level system, okay, N2 is greater than N1. Okay, so 1 is thermally populated, so need to raise a lot of population from 1 to 3. So that is what is done by using the pumping mechanism. Remember, this is a metastable state to begin with. All right. So basically, it kind of acts as a buffer or as a hold where the electrons are populated, and then they have this is of the order of milliseconds before they actually undergo a slow transition to the ground level. You can also do the same thing with 4-level laser systems also. So here also there are 2 buffers now. So you again have the pump which takes it from 1 to 4. Then you have a fast radiation-less transition to 3. And from 3 to 2, you have a slow laser transition. And then from 2 to 1, you have a fast radiation-less transition. So this is basically, there are 2 hold places, 2 metastable levels, and the lasing happens only for photons which match this particular energy transition. Only this, not this 1 and 4, but rather 2 and 3. All right, and here it is of course between 2 and 1. Okay, so this pumping mechanism is not necessarily monochromatic. Some lasers are okay, so pumping need not be monochromatic. We use a flash lamp sometimes, and some lasers have broad emission range also. That can also happen. Okay, but it is not white light per se, but it has got a slightly wider frequency band or wavelength band. Let's look at it in this way, that again, this is the 4-level system. So at 4, this is highly excited. It goes to this metastable state, and then you have the laser emission, and this is the population inversion, and this goes to a lower metastable state, and this is the stimulated emission. So you need photons which basically match energy of these two levels from 3 to 2. Then you have this coherent photons that comes out of it, same phase and same direction. And then you actually have from lower metastable state all the way up to the ground state by using the non-radiation-less decay processes. The same thing happens over here. This is the population inversion that you have, and then you have the fast decay by stimulated emission, which is like a laser burst. This is more used for bursting purpose. This is more used for beam purpose. Okay, those are semantics and more details, but those are also done if you want to get energy throughout the day or something like that. Okay, or at any time if you want it to laze. This will give you energy in short bursts, so to say. All right. So all laser oscillators are opposed to amplifiers. So how you make a laser, you need a gain medium, which is the medium in which these transitions are taking place. They can be gas, solid state, or liquid, which provides the laser transition. It needs to have a pump, the source of energy that is needed to create the population inversion, usually another light source, example, a flash lamp or a laser, or it can be an electric current that is used as a source of energy to create the population inversion. You need to have a source of energy. Okay, flash lamp is most commonly used. You need a cavity, because in this cavity you need to recirculate the photons to stimulate emission or lasing transition. So the photons are basically made to go inside this cavity round and round so that they can knock off more and more photons. Okay, and so often mirrors guide these cavities, etc. So there is a lasing threshold. So when the gain, that is the number of photons emitted in one round trip through the cavity, exceeds the loss due to absorption and due to mirrors, we will see the construction. And when that lasing threshold, when the gain exceeds this, you have a lasing threshold. The gain should exceed the loss. Otherwise, you have a decay of photons rather than an amplification. And whether you want the laser to laze light all the time, like continuous wave lasers, or pulsed. The lasers can be femtoseconds to nanoseconds. Okay? So there are all kinds of lasers that are available. So if you look at just a cavity, that there is a reflector on one side, this is an 100% reflector, and then there is a partial reflector on the other side, which just allows the laser beam to go through. And this is the amplifying cavity. So what you do, you provide the energy input by pumping, and then the photons are basically emitted. So the photons basically knock off more photons in this amplifying cavity in such a way that there is a population of photons of the same kind, of the same coherence. Okay, so what happens is that you pump from medium to upper level, the photon decays spontaneously. So a photon happens spontaneously, and then it stimulates more emission. So because it is knocking off all the loose electrons that are there in this gain medium, because all the electrons which are in that upper energy state. Now, if the number of photons emitted in each round trip through this cavity, because the photons are then reflected, exceeds the losses, because the mirrors are never really, absolutely 100% reflective. So they will absorb a little bit, and there can be other losses also. So if this in one round trip you should have more number of photons, that means your number of photons should go on increasing. So only one of the mirrors will allow a small amount of light to go through. This is what is called the laser output. So the laser output is controlled by the gain of the medium, that means how many number of photons you are getting, and what is the modes of the cavity, that is transverse or longitudinal. because the photons gets knocked off in all possible directions. You can control which, by controlling the length and the dimensions of the cavity, you can control which laser modes to basically pre-populate. Okay? So the gas lasers are usually electrically pumped, wide range of wavelengths, and it has a low gain. Liquid lasers use complex organic dyes. They are tunable also. So that means you can change the wavelength of lasing by changing the dye, essentially, because the medium actually controls which wavelength will come out of it. Okay, the red versus blue versus green, etc. Solid state lasers are the widest class of lasers. The lasing is usually iron doped in a crystalline host, like for example, Nd:YAG laser, TI sapphire laser, fiber lasers, semiconductor diode lasers. So they have a very complex kind of a system. The gas lasers are helium neon lasers are the most common, 632 nanometer. Okay, here you can see how it is done. Okay, so this is the laser bore tube. Then you have the UV excimer lasers. Okay, and then you have the pumps for chemical reaction. Then you also have CO2 lasers. This is used for industrial and medical applications, not necessarily for flow diagnostics. This was sometimes used. Okay, but Nd:YAG is the most common source of laser that is used. This is, for example, the liquid lasers. You can get whatever light you want. This is very important when you actually deal with that. The dye lasers are actually very good when you are dealing with laser-induced process. The solid-state lasers are the most widely used lasers. You have TI sapphire, Nd:YAG is the most commonly one that is used. You also have semiconductor lasers, and we will see semiconductor diode lasers also, which we will see in our EDLS presentation. And the pumping mechanism is usually flash lamps, broadband flash lamps. Other lasers use fiber lasers and also electricity in the case of semiconductor diodes. Okay. And this is TI sapphire lasers. This is a very important laser in the sense it has a bandwidth of 300 nanometer, very short pulses. Okay, this is basically the two energy levels that is shown. It's a little bit more complicated than what we have been taught over here, and it is commercially available in petawatt. This is the workhorse of many scientific research. Again, it is very good for combustion diagnostics as well. Okay, so in other words, we can also have high power lasers, where you can have long pulse and you can have short pulse. Okay, and stuff like that. You can have mixture of laser systems. So basically, whatever wavelength you want these days, we can have a laser which is catered for that. In other words, this is the story of the lasers. Remember, it always works on these three principles, which is absorption, spontaneous emission, and stimulated emission. We need stimulated emission, and this is done using a population inversion mechanism.